to invite Mark Wilkinson to join me here, please. Mark, if you don't mind, I will present you in Portuguese because it will be easier for me, but then I will switch to English.
Join you there or here?
You can... Temos hoje connosco o Mark Wilkinson, de facto é um prazer e é um privilégio tê-lo aqui. Ele é conhecido por várias coisas, a principal eu vou referir no final, mas só umas breves notas biográficas. Ele trabalha presentemente no Centro de Biotecnologia e Genómica de Plantas da Universidade Politécnica de Madrid e é o chair de Biotecnologia, portanto é um investigador sénior de um programa de BBVA e UPM, portanto, da Universidade Politécnica de Madrid, no programa chamado Isaac Peral, portanto, que é destinado a investigadores séniores. Tem trabalhado sempre na área da genética e da botânica, tem um doutoramento pela Universidade de British Columbia no Canadá em Biologia Molecular das Plantas e é professor também de Genética na Universidade de British Columbia e na Universidade Politécnica de Madrid. Mas aquilo pelo qual, digamos, mais recentemente é autor de cerca de uma centena de artigos, também em vários domínios, mas aquilo pelo qual é mais conhecido e a razão pela qual nós o convidamos para estar aqui connosco hoje é porque é um dos coautores do artigo que se tornou o artigo dos 4 mandamentos da gestão dos dados de investigação, que são os princípios FAIR. Findable, Accessible, Interoperable e Reusable, que de facto hoje estão na base, e se vermos toda a maior parte dos documentos que se referem à questão da gestão dos dados de investigação, desde documentos políticos até as questões mais operacionais, os princípios FAIR, de facto, são princípios que foram adotados e estão adotados como de facto a referência para a gestão dos dados de investigação. E por isso é de facto um prazer e uma honra ter aqui o Mark Wilkinson. Eu vou mudar agora para inglês, so I'll switch to English, and I would like really to... I told in Portuguese that you are one of the co-authors of the document that now is like we have the 10 Amendments from the Bible and the 4 Amendments for data management. Yes, that's the FAIR principles. So, and it's really a privilege for us to have you with us today. So I'll give you the floor as initially planned. We would like to have about 45 minutes presentation and then 15 minutes for questions and comments. Thank you, Mark.
I will do my best. If we could reduce the lights a little bit, that would be great, because some of the slides might be hard to see. First of all, thank you very much for the introduction. I trust everything was true. And it's a real privilege to be here. I appreciate the invitation. Thank you very much. And I'm sure that many of you have seen presentations from Barend once before. He was at the end of the authorship list, I was at the beginning of the authorship list, and that reflects our styles. We're very, very different people. He's an evangelist, and I'm a builder. So a lot of what you're going to see today is going to be quite technical about what we built to make the FAIR principles come alive. You are free to reuse this presentation as you see fit. This is the URL to the presentation if you want to use it. So I could have picked any number of statistics, but I picked these two to describe the problem I'm sure you all know. So there was a publication recently of environmental biology and showed that 64% of the data archives have flaws that partially or entirely prevent reuse. And another study showing that 80% of an informatician's time is actually spent finding, reformatting, and integrating, not doing data analysis. And that's only on the 36% of data that's reusable. So the problem is not that the data is useless, the problem is that the data is reuseless. So why do we need FAIR data? Well, we need to solve this problem of reusability. And so a few years ago we published, as you said, these commandments, in a sense, for how to publish data going into the future. At the highest level, they say that for findability, there should be unambiguous identifiers with searchable metadata. For accessibility, there should be a clearly defined access protocol, preferably machine-actionable access protocol. We should use shared vocabularies and ontologies in a machine-accessible data format, data representation format. And finally, for reusability, we need contextual information that allows you to interpret the nature and the purpose of the data, as well as there is provenance to accurately cite. We'll go into a little bit more detail about these in a second, but the consequence of publishing this was almost immediately. Within months, the European Commission had put together this high-level expert group, and their recommendation was, and I'll just read it, to make adequate data stewardship mandatory for all research proposals. Horizon 2020 should only support projects that properly address data stewardship, and those that do not specify fair conditions should not be eligible for funding. That's a really strong thing to say, right? Just a few months after the principles were published. But H2020 picked up on that, and within a few months, they had published their open research data guidelines, and they put fair at the center. So it would appear, if they're going to follow these recommendations, that in the future, if you're not fair, you don't get funding. So we have to figure out what fair is. Because it's defined by a set of principles, but we don't define how to implement those principles. So just to show that there's actually a number of organizations, NIH especially is picking it up, but the African Open Science Cloud and also some initiatives in Canada beyond Europe. And of course the G20 have recently endorsed in 2016, saying that they want all of the G20 nations to adopt the FAIR principles. So let's look in a little bit more detail about what the individual principles say, because that will help guide my discussion of one of the early prototype implementations. So F1 says that metadata and data should be assigned globally unique and persistent identifiers. These data should be described with rich metadata. The metadata should explicitly include the identifier of the data it describes. That one is a difficult one to explain, but we'll see it a little bit later why that's a principle, because it's really quite important. And finally, the metadata and the data should be registered in some indexed searchable resource. For accessibility, you have to be able to retrieve the data or the metadata by their identifier in using a standardized protocol. The protocol must be open, free, and universally implementable, which means that we're not allowing vendor lock-in. If we cannot open and freely and implement this protocol, it's not fair. So that means that everyone should be able to play this game without a company taking over. The protocol allows for authentication. Clearly we need that for private data. And longevity is an important factor. So metadata should be accessible even when the data is no longer. Interoperability says that metadata should use formal, accessible, shared, and broadly applicable language for knowledge representation. There turns out not to be many of those. There's only a couple of options at the moment. The vocabularies that we use should follow the FAIR principles themselves. This is not really recursion. If we're using vocabularies that are not accessible to a machine, then we're not really solving the problem, because the machines cannot understand the data. Neither can humans, for that matter. So the vocabularies that we use for annotation should also be fair. They should be findable, accessible, interoperable, and reusable. The data and the metadata should include qualified references to other data and metadata. What we mean by qualified is that unlike the web, where there's a hyperlink and you click it and you go from one page to another, a machine doesn't understand the reason for that link. And that's why we use the word qualified. The qualified connection, the qualified reference, means that I'm explaining to you the connection, the reason for this connection between this piece of data and that piece of data, or this piece of metadata and that piece of metadata. The reason for that linkage must be described. So it's not just a cross-reference, but it's a qualified cross-reference. You understand the purpose. And finally, we get to the key, which is reusability. That's the objective of this whole exercise. For reusability, you have to describe your data and metadata with a plurality of accurate and relevant attributes. Plurality means more than the minimum. So we are encouraging you to be as generous as possible. Use as many attributes as you possibly can without trying to guess who is going to reuse it and for what purpose. And that's why we say give people more than what you think they need, because you shouldn't judge the purpose of reuse of your data or your metadata. You should provide a clear, accessible data usage license, clearly. detailed provenance so that people can understand how the data came to be and therefore understand if it's useful for their purpose. And finally, beyond all of these basic things that everybody should do, your community will also have standards, and you should follow the standards of your own community. So we give a nod to individual communities, saying that to be fair, you actually have to be adherent not only to the principles, but also to your own community standards. Okay, so what does it look like? Well, at the original meeting where we defined the pre-principles, so this was before the final version of the principles, a group of us got together, and we called ourselves the Skunkworks group, and we were a bunch of hackers, and we said we're going to build a prototype of what we think fair data actually looks like. So this is a solution, not the solution. This is a prototype which fulfills, I think, all of the principles, but it's not the only way to do it. Okay? The participants are quite varied, and we had a series of teleconferences and hackathons. And the concepts that came out were this, that we want a large ecosystem of things that use fair data, and we want a large ecosystem of source providers, and the connection between them has to be very, very thin. Whatever we do to connect the source to the apps has to be fairly simple and thin. Now, the people who were self-selecting in Skunkworks had a lot of experience around metadata and scholarly publication, and there's a list of some of the projects we've been involved in. It's not coming out of the backside of the skunk, it looks like it is, but it's not. So we had a lot of experience in this area, and in fact, during our teleconferences, in the first week, we had already agreed on how to do F, how to do A, and how to do R. That was unambiguous. The problem was I. Interoperability is hard. It's always been hard. It's been the focus of my research for the last 17 years. And I'm still trying to solve the problem. It's hard. So in our teleconferences, we said, right, there's certain features that we think are going to be necessary to specifically for machines, to guide their exploration of data sets. And we came up with this idea that the machine should be able to drill down gradually, piece by piece by piece, all the way from, for example, a repository like EBI, which has many, 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 many different databases, all the way down to this last point, which could be, and in a recent publication I've shown it is, a single data point inside of a data set. And the machine should be able to discover all the way down how to get there and what it's doing. The other thing that we basically all agreed on was that we should not create a new API. Because if we look at the web right now, programmable web has a catalog that includes 16,000 web APIs. And the controversial statement here is that APIs do not make you interoperable. They don't solve the problem, they just add another problem. Because everybody has to code to your API. So, we concluded that we should reject any solution that requires a new API. What we decided on was to use the web standard, which is called REST, Representation State Transfer. I won't talk about how REST looks, but it's a universally applicable standard on the web that uses web technology as its core. So the question then were, are there existing standards that are REST and also have this Russian nesting doll property? Well, it turns out that one had just been published called the Linked Data Platform from the W3C. And I'll take you through the useful features. So first of all, Linked Data Platform uses machine accessible standards and representations that follow something like a REST paradigm. It's actually not correctly REST, but it's close. It does define the concept of a container, which is a machine actionable way to represent repositories or deposits or files and their metadata. It defines resolvable identifiers for each of those containers, and it uses a widely accepted standard called DCAT, the data catalog, to relate the data to the metadata, which allows machine actionable data mining. So let me show you what a fair accessor looks like. We call it a fair accessor, which is Linked Data Platform plus some other pieces that we've added. So first of all, what are we trying to describe? So we want a machine actionable, structured, REST-oriented way to publish metadata. So I'm focusing only on metadata for the first part of this talk. to publish metadata about a wide range of scholarly entities. For example, data warehouses like UPI, databases like Uniprot, repositories like Zenodo or the Read repository, data sets, for example, the output from some workflow, research objects, which are the data, the workflow that generated them, the results of interpreting the data, and the publications, these conglomerate objects that can be published as a unit. Data slices, for example, the database query and the results of that query. Data records, for example, images, patient clinical records, and many other things. So we are trying to represent almost anything in the data ecosystem using the same technology, the same principle. So this is what it looks like at a cartoon kind of level. So in the REST paradigm, you have resources. Resources are simply addresses on the web. Resources in the web context are addresses on the web. So a container resource is just a URL. And a meta-record resource is just a URL. And when you call that URL, you get a document. And this document contains metadata and additional information, and metadata and additional information. So let's go down one level away from the cartoons. So here is the URL, my repository, my dataset /ABC. This is called the container resource. I retrieve it, and I get metadata describing the content of that container. For example, if the resource represented an experiment, the information could be, what is the hypothesis? What technologies did I use? What protocols did I use? What organism or strain did I use? And importantly, citation information. Right? So this container level of the accessor is really the materials and methods in the context of an experiment in a machine-readable manner. And then it says, this experiment generated 3 data records, 1, 2, and 3, but these are links to the metadata of those data records. So here is our meta record, my dataset ABC /URL3. I call that, and again, I get metadata, this time about the record. So, for example, what machine or device generated this data record, what filters or cutoffs were used in that algorithm, what algorithms and what settings and what parameters, and every data file should have a usage license, because they could be different from file to file depending on, for example, which data sets you had to import in order to generate your output. So every file has a data usage license, and then we actually get to the data. So here we have a distribution of this data record at this URL, and the format is in CSV, or I can, at this URL, retrieve it in MS Excel. So I've gone from an experimental level down to a meta-record level, down to the actual data, every step of the way guiding the machine so that it can explore this by itself. So, in what way is this fair? Let's walk through it. F. These are globally unique identifiers for data and metadata. So we have these identifiers which are, by definition, because they're web addresses, they are globally unique. We have metadata that can be searched, even by Google, because we're using web standards, we're not using an API. So a GET, which is what Google does, a GET on the URL will return these documents and they can be indexed. So the metadata can be searched, which makes it findable. Accessibility A, well in this case it's very simple. The web gives us the accessibility layer. Simply call the URL using the HTTP protocol. So we retrieve the URLs, and that's our access protocol. Interoperability, you'll see in a little while what this actually looks like, but this metadata is using a standard called RDF, Resource Description Framework, and OWL, Web Ontology Language. So it's machine readable. So machines can interpret the intent of the metadata that describes the experiment and describes the records. And the vocabularies that we use inside of that are also fair, as required by the interoperability principle. In addition, for enhancing interoperability, these data structures themselves are compliant with DCAT, which is a global standard for representing records and catalogs. So there's a lot of software out there already that can interpret these data structures. So again, we're not inventing anything. almost everything that we've created already existed. We just put it together in a novel way. For reusability, the metadata includes contextual information, license information, citation information, provenance information. Whatever information we think is worthwhile providing, we put into these metadata blocks, which assist with reusability. So, excuse me. So we have this machine directional from the experiment. You find this container metadata record, you go down to that and you get the metadata, and you go down to this URL to get the data. We have this directionality, but we also can layer multiple layers of this. So if you have a repository with many databases, with many data sets, with many data records, we can just iterate this, and this is the Russian doll. So what are the features of the FAIR accessor? Well, first of all, there's no API. You have a resource, a URL, you get that URL, you interpret the metadata, you make your next selection based on the content of that metadata, and you get it, and iterate, and iterate, and iterate. There is no API, there's no interface definition. It's just the web. Get, and you interpret the metadata. So that means that any web agent can now explore a FAIR resource. For example, Google, or if you have a good indexer, excuse me, a good indexer of RDF. Google is not. If you have a good indexer of RDF, the machine can actually interpret it and explore it intelligently. So we haven't invented anything. Our interface is literally nothing. It's nothing. We didn't invent anything. But there are really nice consequences of this. So we actually have defined a way to produce identifiers for things that were previously unidentifiable. There was no way to identify them. For example, a database query and the output from that database query. So I can put into my metadata exactly what the query was and exactly what the result set was, and I can give it an ID. So people can talk about that query based on its ID and say, well, that query is in fact flawed. Right? There was a flaw in the query, and this is what it should have looked like. So people can talk about explicitly my experiment, or the data set that I used to build my experiment on. So this should assist us in achieving reproducibility and transparency, because we now have a way to explicitly talk about a lot of things that we couldn't identify before. We have a predictable place for metadata, and that's important. There's a lot of ways to publish metadata and data, and repositories do it differently. So this actually provides us a predictable place. We know where to go. We know that the metadata coming here is going to be connected to the metadata here, is going to be connected to the data. So there's no ambiguity. But, excuse me, it also encourages that you explicitly separate your metadata and your data. Right? And this aligns with principle A2, that the metadata should be accessible even when the data are not. So if your protocol was that you put your data file and your metadata file into a single folder and publish them, chances are, when the data disappears, the metadata also disappears. And that's probably not a good idea. So this feature of the FAIR accessor encourages you to actually separate the two explicitly. Thank you. Thank you very much. To explicitly separate the two, which aligns with this principle. There's a symmetry that isn't obvious here, but I'm going to point it out. That part of the DCAT specification says that you should actually refer back up from a container. So you have a container with an element, but the metadata of the element should refer back up. And so no matter what you discovered, if you were searching Google and you discovered this instead of this, you would have a defined path to get back up to the citation information. Machines will know how to do this. And so there's an unambiguous path from the experimental or the repository down to the meta-record, and from the meta-record back up to the repository, so that you always have license, citation, provenance. All of this is accessible in a predictable manner. Now this one is an interesting consequence also, that you could provide whatever you want to provide. So we have this interesting access, we have an interesting way to govern access. So for example, here's my repository URL, I get it, and it gives me some metadata about the repository and the experiment, and it says it contains 184 records. Contact Mark Wilkinson for more information. So there's no further access. This is in fact an access protocol. Pick up the phone and phone Mark Wilkinson. It's a perfectly fair access protocol. It does not have to be machine actionable. The FAIR principles do not require that. So this is an access protocol, telephone. It's universally implementable, it's free. Okay? So, but we haven't given away anything. We've simply said, we did this experiment and it contains 184 patient records, and in order to get those records you have to phone Mark Wilkinson. So this is for highly confidential information. If the information is less confidential, a little bit, you can put in the next layer. So now you have these meta records, which we'll talk about individual patients. So we have a patient between the age of 20 and 40 who has some form of heart disorder, but you are not allowed to have the data. So that allows registry federation, effectively. You can do a profile of all of the registries in an experiment, for example, without actually giving away any of the data. And the registry owner chooses what they want to put in here. So that, again, we have confidentiality at this level of granularity. And finally, of course, you could, for non-confidential information, just provide the data. Right? So this would be a fully open access repository. So our way to approach the problem of privacy is simply do nothing. If you don't want to talk about your data, don't talk about it. That's easy. Thin. Okay, so this is what a real fair accessor looks like. So this was published about a year ago, and it's a slice of UniProt that we made for one of our experiments. We were studying the pathogenicity of a certain fungus. And so this was a real-world scenario. We're publishing a paper describing the evolution of proteins in RNA processing in the fungus Aspergillus. And we want to be transparent and reproducible, so we have to describe the inclusion and the exclusion criteria for selecting the proteins in our data set. And again, generally, this is either not done, or it's done in the text of the paper, and you have to read it in the materials and methods section. Right. So here's the query that returns the proteins of interest. So this was the query we did for the paper. We limited it to the taxon, and we said that you have to be a subclass of the gene ontology term called RNA processing. And so if you had your computers open, you could go to this address. It's live. This was a real experiment that we published. So this is the container resource, linkdata.systems/accessor/UniProt accessor. You call get on that, resolve it in your browser or in your software, and it returns a page of metadata. And what I'm going to show you now is what that metadata looks like rendered into HTML. So this is the HTML representation using the tabulator browser from Tim Berners-Lee. So this is what the fair accessor looks like, rendered as HTML. Underneath this is actually RDF, for those of you who know RDF. So we'll zoom in a little bit, and we'll look at some of the details. So this is, again, this is the container resource, the description of my experiment. So the metadata is about me. Right? So this is a UniProt slice for Aspergillus RNA. This is my ORCID ID. This is the number of entries that were returned. Principal investigator Mark Wilkinson. Here is the query that I used to run my experiment. Right? In detail, people can talk about this query by referring to the URL. A little bit farther down, the accessor contains keywords, so literally keywords. These are for the monkeys. And here we have this concept called a theme, which is part of the DCAT specification, and it points to a concept scheme. And a concept scheme is looks like this. It's a list of ontology terms that are aggregated together to describe the content of that data set. So every one of these is a machine-readable concept put together using the Simple Knowledge Organization System, the SKOS. Right. So we have keywords for monkeys, we have themes for machines, so both humans and machines can understand the content of the data set. And finally, we have this list of the records that came back from the query. So this is this part of the top level of the accessor. So now, we traverse down, we take one of those and we use it as the next resource. We call get on that resource, put it into your browser, and this is the document that comes back. Again, what it is fair metadata. It tells you what it's about. The identifier of the data should explicitly be in the metadata. There. And then a series of distributions. So again, zooming in a little bit, and this is critical. This record has nothing to do with me. This record is published by Uniprot, not by me. So therefore, at this level of metadata, the focus has changed. The metadata is about Uniprot. So there's the citation for the Uniprot database. This is the Uniprot record. It's not about me, it's about Uniprot and their records. It's theirs, not mine. But here's the upwards link. The DCAT says you should be referring back up to the dataset. So in dataset Uniprot accessor, that's me. That's the container resource that has the attribution information for me. So there's a symmetrical link back upwards in a predictable place. And then we have these distributions. So there's a distribution in RDF format, and there's a distribution in HTML format at two different URLs. Both of them are in fact provided by Uniprot. They are the publishers of the RDF and the publishers of the HTML, so we point out to their database. So, this is what FAIR looks like in the context of Uniprot. And Uniprot is already pretty fair. They're pretty good in their RDF publication. But this is even more fair because, for example, the license for Uniprot is not part of their records. There's no reference to the license in their records. So to find their license, you have to search their webpage. So here, we actually include the license information in the meta record. So it's a little bit more fair than Uniprot itself. Okay, so what do we get from this? Again, what have we achieved? Well, now we have a fair record for something, for example, the slice of a database, that was historically not recordable or identifiable in any formal way. There was no formal way to do this. So that's with respect to F. With respect to F and R, accessors are a standard approach to providing both human and machine accessible metadata in a predictable location that facilitates discovery and proper usage because we have a license and proper citation for any kind of data. F and A, the discovery, accessibility, and drill down and drill up does not require an API. It's just web. This is all web. So it can be indexed by any existing search engine. The metadata for I, the metadata uses machine-accessible syntaxes, ontologies, and vocabularies, so we can integrate it with other metadata. For A, the accessors are lightweight means to protect privacy while still providing transparency at whatever level the repository owner wishes. And plus, accessors can be static or dynamic. So these are actually not difficult documents to provide. They're quite lengthy, but they're not hard. We can templatize them. So I have, in fact, created an accessor in Windows Notepad using a template with XXX's in the places that I have to fill in information. So these are documents that can be edited manually, or you can dynamically interrogate your underlying data source and project out a fair accessor using code. So they can be dynamically or statically produced, which means that I can create a fair accessor, and I can show you the reference, into a Zenodo deposit. So I have my data and the fair accessor in the same Zenodo deposit. Okay, so far, everything has been about metadata. And so at the end of this talk, we're getting close to the end. I don't know how I'm doing time-wise. Are there approaches to making the data fair? So I came up with this idea called fair projection, which is a way to dynamically generate fair data from non-fair data. And is aimed at non-experts. So we could hire thousands of verifiers and get them to go through Zenodo and transform all of the data sets into an interoperable format, create fair accessors, and then republish all of that data. That would be silly. Or we could community source this and say, community, we are going to give you a tool where you can transform non-fair data into fair data, whichever pieces of that data you need at whatever time you need it, and at a click, publish it for everyone else to use whenever you want. And it will become permanently republished. And you can get cited for that. So here's the scenario. Imagine that the data that we need to integrate for our question of the day, whatever the question is, we need to integrate certain data, and darn it, it's in a CSV file in Figshare or in Zenodo. Now what do we do? How do we discover and integrate that data? Well, there's a lot of things we need to do. We need a way to query opaque data blobs like CSV. We need a way to retrieve that data in a fair format. So therefore, we need a way to model the semantics of that opaque data. I'll take you through an example in a second to explain all of this. But one size does not fit all. Some people in the medical field like to use ICD-10. Other people like to use ICD-9. Other people like to use SNOMED. Other people like to use mesh diseases or the disease ontology or so on. So there's one semantic will not fit all scenarios. So we need to model various transformations of that CSV data into various ontological formats. We need to associate the semantic models with particular record sets, and hopefully in a reusable way if we can, so that people don't have to reinvent the models. We need a way to query the semantics to decide which of the semantic representations is the one we need. And again, we need to make it reusable. And we need to do all of this without inventing a new API. So again, there were two new technologies that had just appeared. One from Ruben Verboer in Ghent, called the triple pattern fragments, and the other called our RDF mapping language, RML, from his colleague at Ghent, Anastasia Demou. So this, again, is very recent, 2016, June 2016. And what triple pattern fragments is a REST interface for retrieving and requesting triples from any format of underlying data source. And so what a triple pattern fragment is a URL that represents a slice of data. A slice of data. This column of this data set, this row of this data set, this cell in an Excel spreadsheet. Everything is given a URL. And what TPF does is it defines what those URLs are going to be. So for example, if you have a body mass index column in your patient, then your URL might look like this, where this component of the URL you shouldn't ever have to see, but I'm going to tell you what it means. CMO 00105 is the clinical measurements ontology term for body mass index. And what happens is that the triple pattern fragment server goes into the data, finds all of the entries in that column, and gives them to you in RDF format, together with additional URLs, suggestions. Like, you might also be interested in this row or this column, which is, for example, CMO 004, which is systolic blood pressure. So it gives you the answer and some additional suggestions for further exploration. And if you continue following these suggestions, they're actually quite intelligently provided. You will eventually explore the entire data set. But at first, you can search for exactly the slice that you want. And this is what REST is. No APIs. Just addresses and metadata about what the address means. So we have a standard RESTful way to request triples, which is a fair data format, from any data source. This is good. So every slice of every data set, including images, by the way, I'll talk about what that means in a minute. Every slice of every data set or every data file is considered a resource, and we just call get to get the triples. But at the moment, we still don't know what triple pattern fragments resources are going to be available for any given data set, or what those resources actually mean. We have no way of defining at the outset this URL that represents that slice. We have actually no way yet to define what I am going to get when I call that slice. So we have to fix that problem. And that's what the second technology is called RML. So RML allows us to create a meta-model of a data structure. So I'm going to phrase it very carefully. What could this data look like if it were mapped into RDF? So this is actually, probably a lot of you in the room will know the metadata registry's ISO standard. And this is actually one of the objectives of that standard, and it fulfills those objectives quite well. So it is a meta-model, one of potentially many for exactly the same data slice. Remember, different ontologies, different semantics for different people who want to use ICD-10 versus SNOMED. So what could the data look like if it were mapped? This is what RML looks like. I'm just going to show you the three critical parts. It says the subject of the triple is going to be a patient record, the predicate is going to be has variant, and the object is going to be SNP, single nucleotide polymorphism, and it also tells you the actual structure of the URL. So it's describing the structure of a single triple. We call this a triple descriptor, and it says this is what the structure of your slice is going to be. But it also tells you the semantics. The semantics are that this is going to be a patient record, and this is going to be a SNP. And it tells you which ontology you're going to use. Right, so this is what the data looks like, and this is what the meta-model looks like. So now we have a way to request triples, and we have a way to describe the structure and the semantics of those triples, but we still don't have a way to associate those with each other. So, and we also need a way to associate those, associate those with the data set or record that you're going to project. So in fact, we've already solved this and you've already seen it. The fair accessor already does this. Right? So we say, look, DCAT says that you can have distributions of a record. So at this URL, you get RDF. At this URL, you get XML. So if our projector, if our triple pattern fragments resource is just another distribution, then you simply stick it on the end of the existing distribution and say, okay, you have RDF, you have XML, you have Microsoft Excel, and you also have RDF coming from this URL, which is another way of representing the same data. So it's the same record represented in a different way. So this is the URL representing the triple pattern fragments resource. And then we add the model. We say, and by the way, this is what it's actually going to look like. This is the URL to this model. And you put those together. Record R, for example, by CSV file in Zenodo. Distribution, CSV. Distribution, RDF. I now have a new distribution of the same file, dynamically generated. And we call that a projector. So the projector says, if I call get on this URL, I'm going to get RDF XML triples, fair data, from record R, which look like this. Okay, I skipped one thing. Those triples do not magically appear. This is not magic. Right? We have to actually create them. Somebody has to create them. So what I'm talking about is this. That URL has to somehow generate triples from a CSV file. And there's no magic wand. Somebody has to do that. But, not magic. This is not going to come for free. But let me walk you through the thinking about what we've done. Researchers have to transform their data anyway. What they do now is they download it and they transform it and probably load it into a local data store. They have to do the transformation anyway. So, we're not asking them to do anything more than they're already doing. Number two, for the most common file formats, so CSV, Excel, and other formats that I won't get into, there are tools already that will automate the transformation. You build a model in RML, and you point it at the file, and you say, please convert that file into this model. And there are tools that will almost completely automate that. Now, investing time into creating a model versus investing time into transforming the data is actually more fair, because your effort in transforming data is reuseless. Your effort in building a model and publishing it at a URL that other people can use is reuseful. That's fair. So investing your time into building models instead of doing data transformation is fair. And you can get citations, citations, citations. People can use your models. We're talking about microcredit in this community. This is one source of microcredit. These accessors and projectors are fair objects and can be cited. You are part of the citation information. And finally, RML triple descriptors are really very simple. They're just one triple. You don't have to be a semantic web expert to create one triple. And we can templatize their construction. So creating a fair projector is so easy. How easy is it, you say? Let me show you. I was at the Biohackathon in Japan last month, and in 3 days I built the following piece of software. This is a really hacky prototype, but I just want to show you how easy it is. This is the first prototype for end-user generated fair projection of data from Genómica. So the objective was, we take hard-to-reuse data and we change it into reusable data in a way that's findable, accessible, and interoperable. So here's Genómica. Here's a deposit of a CSV file in Genómica. This is, you've all seen Genómica, I'm sure. This is a quick preview of what the data looks like. And let me show you the problem. Right? This column is called entry. This column is called entry name. These are not informative headings. Can anyone tell me what that is? What does it represent? Are there any biologists in the room? No. So this is reuseless for you. You have no idea what these IDs mean or what these IDs mean. Right? Now I'm lucky, because I drink and I know things. I can look at that file and I said, well, actually, I know this pattern. I'm familiar with this pattern. These are actually identifiers from the UniProt database. So I know that if I put those into this URL structure, I'm going to actually get to the UniProt records. So I know that. I also know, I recognize this identifier structure, that these are the entry points for the SNP effect database of human phenotypic variations. And I know also their URL structure, or I can look it up. So, because this was at the Biohackathon in Japan, we have a tradition of making Japanese-styled interfaces just for the hackathon. So that's why you have the anime character here. But basically, this is what happens. You put your URL for the CSV file into this box. It then does a quick profile of the content, and it says, okay, this is what I see. It says, it numbers the columns, so you can see how many columns there are going to be. And it says how many lines are headers. It turns out that's an extremely difficult thing to do automatically. So you actually have to tell it one header line. And then it asks you 3 questions. It says, which are the 2 columns you want to project, and what is the relationship between them? So, column number 1 is the column I want to project. I know that the structure is identifiers.org/uniprot/ whatever the content of that column is. And then I start typing in here, and it gives me a type ahead on a lookup over all of the ontologies in the ontology lookup service at EBI. And I say, aha, Unicron ID, that's what that column is, that's its semantic type. Done. Next one, column 2. This is a snip effect, blah, blah, and I start typing in phenotype and I do a lookup, and the type of data is phenotype. And there's a lot of different phenotype entries, you'll notice, but I happen to like the semantic science integrated ontology, so I'm going to choose that semantic as my representation. I can choose whichever one I want. And finally, please tell me the relationship between these two columns. The relationship is a has phenotype relationship from Sire. And again, is this type ahead? It does a lookup and I simply click. And then there's a button, create my projector. If you drink and if you know things, you can do this in about 60 seconds. This takes almost no time. Click. And this is what comes back. So here is my projector URL. If I call that, if I put it into my browser, I get fair data from that CSV file. It also creates the fair accessor for me, and it can do this quite intelligently in the future. It doesn't yet, but it will actually scrape the metadata from Zenodo and add that metadata into the fair accessor. But the fair accessor contains, the metadata about me and about the data file. It can be submitted to a searchable registry. It contains all of the semantic information that describes the projection of that data from CSV into fair formats, which allows discovery of this projector. Here is the fair data, which is another distribution of the Zenodo CSV file. It is now registered as a new source of distributed data from that Zenodo file. If I call the URL, this is what it looks like. Identifiers.org, blah, blah, blah. This is the resource file 1229, which interprets as this uniform record relates to this phenotype at this address. So, again, this whole process took less than 2 minutes. Much less than 2 minutes. But I can immediately integrate this projected data into a query that combines, that federates this new data with EBI, NCBI, PubMed, Kemble, whatever data source you wish. I don't think I proved that, no I don't. But in fact I have some slides that show exactly that working. So you can in fact just type the Sparkle query and your new data will appear. So, we're coming to the end. Summary. Fair projectors provide a discoverable standardized REST interface to interoperable data and metadata. They can convert non-fair data into fair data, change the structure, change the URL format of the semantics. You can deploy them over anything, static data deposits, databases, triple stores, and certain types of web services. And they're independent fair entities that are intended for reuse, and you can get microcredit for reusing them, and none of this requires a new API. It's all get with metadata. And finally, one last statement. We've just finished constructing a set of quantifiable metrics for fairness, and we'll be publishing those in the next few weeks. So if you want to know how fair you are, there will be a quantifiable way to measure that soon. And that's all. So we've talked about fair, Russian dolls, the projection, and the projector builder. So the forecast is cloudy, but increasingly fair. Okay, I will stop because I think my time is up. Thank you.
Thank you very much, Mark. I think we have time for questions. Is there a microphone? Yeah. You might ask in English, or if you don't feel comfortable, you can ask in Portuguese and I will translate to Mark. If there is no immediate question, I will make a non-technical question. Is that you already kind of addressed it, but I would like to have your elaborate a little bit more. I see the value of all these approach, and especially the FAIR projector, but there's still I think a big challenge on getting the buy-in from researchers to use tools like the FAIR projector or others to verify their data. So what do you think it's needed to get FAIR on the daily work of researchers, apart from the declarations and all the guidelines, to really start to have FAIR data, both on the new data that is produced or the existing data that is already on repositories and we want to reuse?
In English, we have a parable, a story about the donkey, and you can either hit it with a stick or you can bring it with a carrot. And we've been trying for 2 decades to lead with a carrot, and now the EC is saying no, you don't get funding. So I think that's how you do it. The carrot didn't work, and now the EC is saying enough. You must do this or you will not receive funding. So I think that we will not have a choice. So the challenge now is that we have to get the tooling ready for people to use before it becomes a requirement of the EC. So we are working as quickly as we possibly can to get that done. But on the plus side, one of the recommendations from the expert group was that the funding for making FAIR data within a project should be a separate line item. It should be calculated at 5% of the total budget of the project and completely independent of the project. So you talk about the science, and then you take 5% of that and just add it as an extra line item. And so it will scale up with the size of the project, and there will be dedicated funding just for that, which cannot be used for anything else. Presumably, if they follow the guidelines that the high-level expert group gave them, this is how it will probably work. And so it's not something you're going to have to do within your existing budgets. You will have funding to hire people, either professional corporate people, or hire students, or give money to your local library resource, however you wish to spend it. But it's not going to be something that's not funded. So I think the stick is where we're going, but it's a stick with some money, which is okay.
Hello, I just have a quick question regarding where does authentication authorization fits in your model? Talked at the beginning, but then you more or less presented it was all open or closed, phoning someone. So I think we can have the many examples where I can give free access to thousands of people, but not the whole world. Like I can give access to people in my community, in my institution, at least for a couple of time, and then later I can open it, or I can just control. I want to control each community can access the data because they have to sign something. How can I? How does that fit your model?
Right. So the accessor is a way, not the way. Right? So whatever mechanism you currently use is what you will use. Right? So the provision of metadata to explain why I would want to phone you or email you to get access, that's completely fair. Right? The access protocol is send you an email and get a username password and pay a license fee. And then the next step is the data inside will hopefully be fair also. But that step of protection is entirely up to you, and we have nothing to say about it. It's none of our business. Whatever technology you currently use is perfectly fine. The important thing is the discoverability. It's important for me to be able to know that I should contact you, that you might have data that's useful. That's really what we're trying to achieve. And that's why we have this multiple levels of granularity. That maybe you can tell me that you have 50 records of a patient with disease X and 20 records of a patient with disease Y, although maybe you can't, because maybe that disease is so rare that even saying you have it is identifiable. So we have these layers of granularity where you can tell me as much as you possibly can to let me know that I should contact you. But you don't have to tell me anything more than that.
Hi Mark.
Hi.
I also have a question, or to have some advice from you. So you said that the eye is the big problem, the interoperability part. So we have some of the participants here are trying to are in charge of manage repositories, or are trying to build repositories to provide services, research data management services for researchers. So what are your main recommendations to that part of the fair accessor for repositories? What are the bugs that you find in the software platforms that we have available for repositories, or the recommendations that you can give us?
I think the big take-home message for me in building this prototype, the big take-home message for me was to stop making new APIs. Like, just stop. Because every time we make a new API, we have to write new software to access it, and it just perpetuates the problem. We're getting to the point where we have enough vocabularies and we have enough good, well-defined data structures that you can use a pure REST approach. So I think that would be my big take-home message.
Any further question? If not, thank you very much, Mark. It was a very interesting talk. We will make a break now.